Do you have any announcements or anything before I start? Or?
Not that I can think of.
Okay.
Hold on, Jerry. The deadline for homework 4 got extended to Wednesday, right? I'm not sure. Okay. Well, if we do have an announcement, we'll
Do it at the end. Okay. Okay. Good morning, everyone. I'm not Biksha. I think you knew that. I'm Graham Newbig. I'm also a professor at LTI, and my main focus is natural language processing, machine translation, et cetera. And this time I'm going to be talking about sequence models and attention. I very much admire you for being up at 9 in the morning every 2 times a week to be here, because I'm not the best at 9 o'clock in the morning. So. Okay, so I'll be talking about sequence models and attention. I think up until now, you guys have covered RNNs and stuff like that. So first, to give a few preliminaries, language models. Have you covered language models at all? No? Kind of. Okay, well, so language models are basically models of text that calculate some probability P of X, and then you can do stuff like sample sentences or something from this probability. So I have an example of this. This is where you train a language model on Harry Potter, and then ask it to generate random Harry Potter. And it says, the Malfoys said Hermione, Harry was watching him. He looked like Madame Maxine when she strode up the wrong staircase to visit himself. So you can see this is not a Harry Potter book that you would probably particularly be interested in reading. But you can generate text that looks relatively good. You can also use this probability distribution to do things like decide which text is grammatical. So that would be useful if you wanted to, for example, take the output of a machine translation system and rescore it based on how natural looking the sentences were. So in order to do this, the way we calculate the probability of the sentence is we have this sentence X. It consists of words X1 to X big I. And every time we calculate the probability of the word, we condition it on the probability of the previous words. Or we condition it on the previous word. So this is the next word, and this is the context that we're calculating the probability based on. So the way we do this with recurrent neural networks is we have our initial state in our recurrent neural network. This I assume you're familiar with. Usually we set it to a 0 vector or something like this. Then we input the start of sentence symbol. And we run this through an RNN to get an updated hidden state. And based on this hidden state, we predict the word I. Then we feed n back in based on this. We update the hidden state of the RNN again, and we predict the word hate. And we step through the sentence like this until we get I hate this movie. So basically, at each time step, we're predicting input the previous word and predicting the probability of the next word. And the way you predict the probability is with a softmax, which I assume you guys have covered also. So this is what a language model with a neural network looks like. And then the main thing that I'm going to be talking about this time are something I call, that are called conditional language models. And these are also called things like sequence models or neural machine translation models also. But the reason why I'm calling it a conditioned language model or a conditional language model is because this idea is a lot broader than just, say, translating between one piece of text and another piece of text. But basically, you don't just randomly generate text according to some distribution. You're also conditioning on some information that comes in as well. So we have input X and we have output Y, where the output Y is basically text or more broadly a sequence of discrete symbols. And X can be any number of things. So X could be structured data. The output Y could be a natural language description of this data. So an example of this would be you have a weather. You have information about the weather in Pittsburgh, and you want to generate an English description of what the weather is like. It could be English. The input could be English. The output could be Japanese. So this would be a translation system. Document short description, utterance response, image text, speech transcript. So we have tasks. I already gave away the first two. It's natural language generation and translation. Any idea what the other ones are? Summarization, yes, very good. Pretty close. This is dialogue response generation. So you can take in something that a previous person said and generate a response to that. Image and text, yeah, captioning, and yeah, transcription. I assume this is a giveaway, given that Biksha is the lecturer of this course. So it's speech recognition. So, has Biksha talked about speech recognition very much at all? Oh, okay. Okay, so there we go. Yeah, I was going to say if he didn't, I'd be a little bit worried in the other direction. Okay. So basically, my point here is these are really broad. You can apply them to a bunch of different tasks, and they're very useful. So they're also relatively simple if you just look at the mathematical formulation, which is up until now, we were creating an unconditioned language model where we just calculated the probability of the sentence, the output sentence itself. But in this case, we're adding some context. We're adding the context that we would like to condition our model on. So every time when we calculate the probability of the next word, we're calculating it based on the words we previously generated plus the added context. So a very simple variety of these models was proposed by Sutskever et al. In 2014. And basically what they do is they just have two recurrent neural networks. The first recurrent neural network reads in whatever we want to condition on. So this is called the encoder. And so we input, for example, a Japanese sentence, and we read it one token at a time, calculate the hidden representations. And then the output, the actual language model part, is called the decoder. And the way we connect these two is basically after we've read in the entire input sentence, we have a hidden state here. We just initialize the decoder with this hidden state. So it's extremely simple. If you know RNNs, if you know how to implement RNNs, you can do this yourself. But it still, I think very few people thought this would have worked. So when this paper showed that